All right. Deep learning. The bootcamp is called Zero to Deep Learning, so that's what you're all here for. Let's get started with that. So, why are people so excited about deep learning? Okay. It's because of a competition, a data science competition similar to this one you've just done. Okay, that happened for every year for the past 10 years or so. Okay, the competition was to classify objects in images. 1,000 different categories of objects, 1.2 million images. Everybody can compete. Who is the best? Okay? And up until 2012, this was considered one of the domains where humans do it better and computers will never be as good. Human error, if you take a pool of humans and ask them to classify those images, human error is about 2-3%, okay, on that set. And machines, up until 2012, were scoring with errors up to like 25%. So way worse than humans. And then 2012 arrives and a team gets a model with 16% error. And keep in mind that in the previous years, it had been like a 1% increase per year. So people were, computer vision experts, years and years of research, features that are super specialized, and you get 1% increase, and then the team comes and say, hey, we trained it on a neural net with a neural network, and it scores at 16% error. Wow, the world takes notice. And then between 2012 and 2015, progress on the technical side, progress on the algorithm side, many teams work on it. You get to superhuman performance, so beaten the benchmark of humans. 2015 to 2019, it's basically such a routine thing that we can teach it in a bootcamp. No magic at all, okay? And that's in less than 10 years. That's the speed at which AI is advancing today, narrow AI, this kind of AI, okay? Not only that, but neural networks can tackle slightly weirder machine learning problems where, for example, you want to go from an image to a description of the image. What is that? Is that a classification? Is that a regression? Like, what is it? It's very clearly an input-output problem where the input is defined and the output is defined. But it's not really clear that it's a category. Like, it's more like, I'm not sure how we define that, right? But it's a very clearly supervised learning problem. Only the output domain is a bit broader than what we've learned so far. And what the decision, try doing this with the decision tree. How would you do that, right? Speech synthesis, same idea. You got sound in input and you got speech recognition. Sound in input and text in output. Older approaches were like built on years and decades of like sound engineering and signal processing and a lot of expertise there. And then neural networks come and they do end-to-end speech to text with a higher performance than traditional models. It's simpler to build. Boom. That's what powers your Siri, your Alexa, your Google Now, your everything is this now. Machine translation, another field which historically, had seen a lot of research. You had dictionaries in the beginning, and then you had lots of complex models that are parsing the sentence, figuring out who's who, what's the subject, what's the verb, etc., and trying to build a translation. And then, neural networks arrive and say, scratch that. Just give me the sentence in input and the sentence in output, and I'll figure out what's in between. Okay? So that's the power of neural networks. They do end-to-end machine learning between very complex and rich data sets. Medicine, we are at the point where we do not only like automate diagnostics. This is an example of automated retina disease machine learning, but we help scientists do novel discoveries. What happened here is like, I find it really intriguing. They started with a data set where the input is a set of photos of the back of the eye, the retina, and the output is a label sick or not sick. And the question is like, can we build a neural net that detects whether the person has a retinal disease? Of course, yes, that's the answer. And so that's a big thing, because you can automate this, for example, in countries where you don't have access to many ophthalmologists or like machines. You take a picture of the eye, send it to a service online and get the response about whether it's sick or not. But the interesting thing is, for example, once you have this data, you can ask questions that doctors have not asked before. For example, can you predict the age of a person from the retina disease? Well, you have the data of the patients, right? No doctor has ever wondered if that's even possible, but you have the data. Can you train a neural network to predict the age based on the picture? Turns out you can. And so doctors are like, oh wow, we didn't know that retinas contained age information. Can you train them to recognize sex? Yes, you can. We didn't know that. So what's so special about neural networks that makes them different? So for large enough neural nets, one thing is like their learning curve does not flatten out. The more data, the more it will keep improving with increasing amount of data. The other and maybe most important thing is that you can do end-to-end learning between arbitrary inputs and arbitrary outputs. And so instead of having the complex pipeline that we just built, where if you start to have maybe a speech recognition engine, you will have feature extraction and then acoustic model and then language model and so on. You do end-to-end. Sound in, text out, let the network figure out the rest.